So welcome to my channel on technology space with machine learning and artificial intelligence. So the today's topic is navigation strategy for underactuated ships. This is also part of the playlist of maritime technology. So let's try to discuss why this is an important concept in a navigation system. When you try to control large-scale vessels or vehicle, that controllability cannot be obtained simply by developing an advanced controller with its relevant robustness or stability. The actuation capabilities of these navigation systems, especially whether they are under underactuated conditions, as well as the environmental effect on these actuation capabilities, should also be considered while you are developing a navigation strategy towards these type of vehicles or vessels. Especially when you're talking about autonomous navigation, these underactuated conditions can introduce additional challenges into these navigation systems. So let's try to develop a driving strategy for an underactuated car, and that may relate to the shipping industry in a more later stage. So here I am referring to underactuated car as a vehicle that may not have a so strong brakes. So that means when a driver decided to stop that car, it won't stop right away. It would take some time and some distance to stop. So that's what I am referring to as underactuated car in this situation. So let's think a situation. This vehicle is driving in the speed of V1, and then at that point the driver has decided to stop this vehicle near the lamppost while he was driving in this speed of V1. So what he could do as the next step? So the driver has decided to press the brakes at this point because of the reason he wants to stop that vehicle near the lamp post. So when he press the brakes, the vehicle will achieve this deceleration rate, which is denoted as AB in this figure. Since the vehicle may not have strong brakes to stop this vehicle right away, so because of that reason, even though the vehicle is decelerating, still it could pass this lamppost in the speed of V2. You should note that V2, the speed of that vehicle V2 is somewhat less than the initial speed of V1. So eventually that vehicle will come to a standstill after some distance and time due to these underactuated conditions, and this is somewhat away from the lamppost. So what should be the next strategy for this vehicle? Then what the driver can do, he changed the gears. That means he put it into the reverse gear, and then he accelerate towards the lamppost. And when he achieved adequate speed, when he decided that speed is enough to achieve the lamppost or the drive towards the lamppost, what he could do, he start pressing the brakes. So therefore, again, the vehicle start to decelerate in the rate of AB. So since the brakes in this vehicle is not so strong, there's a possibility this vehicle may pass that lamppost in a much reduced speed in this situation. So I'm referring to that speed as V5, and then it is having the same deceleration of AB. So then again this vehicle may come to a standstill after some distance from the lamppost, but this distance may be less than the initial location of the vehicle. So again what the driver can do, he can accelerate towards the lamppost, and in between the when it's achieve an adequate speed, it can decelerate towards the lamppost. So doing this type of iterative process, eventually the vehicle can come to a standstill at the lamppost. So it doesn't matter whether you are talking about a vehicle or a vessel, not just the advanced controllers, but also navigation strategies should be developed to overcome navigation challenges in this underactuated system. Especially these navigation challenges may related to the safety issues in these systems. So when you come to underactuated ships, I think we have done a good discussion previously on that. So there are 2 videos available in this topic. I would recommend you to go through that, and I would place those video links also in the description of this video. So as a summary, we have mentioned that the ship controllability is a challenging problem, especially controlling the forces coming from the sway direction. In addition to that, this apparent center of gravity as well as this estimation of the course speed vector can be challenging, because these parameters may not be able to measure directly. Rather, you have to do estimation on that. So when you're doing estimation, these estimations may not always going to be accurate if you don't have accurate measurements or direct measurements from. So let's move on to the main topic of this video, which is the navigation strategy for underactuated ships. Before we get into that discussion, let me say a little bit on the ship controllability issues, because these controllability issues eventually influence the navigation strategy of these ocean-going vessels. So the first 2 topics would be apparent center of gravity and the ship under actuation. I think I have done a discussion on that, and I have 2 videos, and please go through with that if you're interested in these 2 topics in more detail. So the third one is heading and the course speed control from rudder, propeller and thruster system. You know, when vessels are navigating in high speed, these thrusters may not respond really well. So having this rudder and propeller system controlling both heading and the course speed vector can be challenged, especially under moderate or rough weather conditions. So then these vessels are massive inertia units. I think this is what the mass is about. Having a larger mass will create this larger inertia, and we are not talking about the smaller autonomous surface vessels. We are talking about full-scale ocean-going vessels. So these massive inertia units or the massive inertia conditions can make challenges in controlling these vessels. In addition to that, these vessels can be considered as slow responsive systems with considerable time delays. So when you have really advanced control, and if you want to make a rudder or propeller actions really fast within these vessels, that may not be possible due to this responsive time and the related time delay in these systems. In addition to that, there are unexpected and undesirable motions these vessels can encounter due to these environmental conditions. And I have mentioned these vessels have this 6 degrees of freedom. So there are 3 translational and 3 rotational motions can be obtained by these vessels. So eventually when you have a complex environmental conditions, you would encounter this 6 degrees of freedom in these vessels. So finally, when these vessels are navigating in a slow speed conditions, some situations it may lose its maneuverability. That means the rudder may not respond due to the slow speed conditions of these vessels. So now you can imagine, other than these underactuated conditions, there are additional challenges can introduce into the controllability of these vessels. So when you're developing navigation strategies, these conditions should also be considered. Let's consider a simple ship navigation situations to explain the development of a navigation strategy. Here I am considering vessel navigation under an incoming wave field. So the navigational requirement is to navigate this vessel from waypoint A to waypoint B. So during this voyage, there is an incoming wave field which is coming from the bow but more into the port side. So the force diagram acting on this vessel is presented outside in this figure. So therefore the vessel is using the propeller thrust to counter the ship resistance as well as the wave resistance in the incoming waves. So as a result of the propeller thrust minus the ship resistance versus the wave resistance in the incoming waves, there would be a resultant force which is also denoted in this figure. So this resultant force is acting on this vessel itself. So due to that resultant force, there's acceleration. Then as a result of that, there would be a velocity or the course speed vector for this vessel. So the course speed vector in this vessel is denoted by V. So then you should also noted that there could be a movement due to these incoming waves. So to counter that movement, the rudder being turned into the port side in this vessel. So let's consider the first navigation strategy as heading control. So the heading vector is represented in this figure as H. So the vessel is navigating with a constant heading throughout this voyage. So you should note that due to this resultant force, the vessel is having a course speed vector which is away from the waypoint B. Because of that course speed vector, the vessel is start to drift away from the waypoint B. So what could eventually happen? This vessel eventually end up in the waypoint C instead of the waypoint B. So that is not the voyage you want to achieve in this type of a situation. So this is an example when these additional forces are influencing these vessels, the heading and the course speed vector can have two different directions. Because of that, it may not be able to complete the voyage the vessel is required to do. So let's consider the second navigation strategy for this vessel. So under that, this vessel is executing constant heading for a sector of its voyage. So because of that, it would come to a waypoint C. So this A to C consists of the sector of the total voyage in this vessel. And then it turned against the wave field. So let's try to explain the force diagram for this ship navigation condition. As you have noted, the heading vector is exactly opposite of the incoming wave field. So due to that reason, the propeller thrust minus ship resistance also pointing parallel to that heading vector, due to the reason that the propeller is also working against the incoming wave field. So the incoming wave field is creating this wave resistance. So if you assume that the propeller thrust minus the ship resistance is larger compared to the wave resistance of the incoming waves, there would be resultant force which is heading towards the propeller thrust, but it is somewhat lower than the propeller thrust. So that resultant force also is the one going to force these vessels to move forward. You should note that this resultant force create the course speed vector in this vessel, and the both heading and the course speed vectors are in the same direction in this situation. However, the magnitude of this course speed vector may not be large as the previous situation, because since the vessel is completely working against the wave field, this vessel may consume quite a lot of energy to create this course speed vector in this situation. You should also note that rudder actions may not required in this situation, because the incoming the force, the wave resistance of the incoming wave may not create a yaw moment on this vessel itself. So this vessel can use the same navigation strategy to complete another sector of the voyage, which is denoted by CD. And then eventually the large sector of the last sector of the voyage, which is denoted by DB, can be completed by utilizing the previous navigation strategy. So if you are looking into a summary of the navigation strategy used in this voyage, actually we have used different navigation strategies to the different sectors in this voyage. So that means there are space to optimize these navigation strategies, especially under each voyage sector. So let's consider another navigation strategy for this vessel. This is called the course control. However, this may not be practical in some situations. So the objective is to have this course speed vector pointing towards the waypoint. This can be a challenge because we may not be able to estimate this course speed vector accurately in some situation. But let's get into a little bit more detail on this type of a navigation strategy. So here I am considering the force diagram for this navigation situation. So as you may have noted, the heading vector and the propeller thrust minus the ship resistance force should be in the same direction. So that is the whole objective, to have these specific heading directions to make that course speed vector pointing towards the waypoint B. So as a result of this propeller thrust minus the ship resistance versus this ship resistance from the incoming force, there would be resultant force which is pointing towards the waypoint B. So this is what that resultant force is, and then eventually that resultant force create that course speed vector in this vessel. So this course speed vector will drift this vessel towards the waypoint B. In general, this is a good strategy, but the challenge eventually could be the estimation of the course speed vector can be a challenge. So that's the end of this presentation. Hopefully you have enjoyed that. So if you are still interested, please stick around. Eventually this concept will be connected into this main topic of the autonomous shipping. So see you in a later video. Thank you.